So one of the things we want to do right now is we want to practice identifying some unknown compounds. Again, we are not going to get the certain identity of any of these compounds when we're done. We have to use IR in conjunction with another spectroscopy technique. It's good to approach these in a systematic fashion. If you look here, and I really love how this is done, this is a stepwise kind of way to attack IRs. The first thing you need to do is you need to identify peaks above 1400. And that's just going to tell you whether certain bonds are present. You need to make sure that you're looking for alcohols, NH bonds, C double bond O bonds, alkenes, alkynes, nitriles, and almost every compound you have is going to have a CH. Then you need to look at different functional groups that have more than one type of bond that you identified in step one. So for example, if you have a carbonyl and an OH, could that be a carboxylic acid? If you have a carbonyl and an NH, could there be an amide, right? Could there be an aldehyde, an alkene, or an aromatic group, a terminal alkene? So look at some of those combinations that we talked about in the previous screencast. Then you also need to look for your special characterizations. Is the OH absorbance consistent with an alcohol or carboxylic acid? Could the NH absorption be an NH or an NH2, right? We're not going to see any absorption if there's no, we're not going to see an NH stretch if there's no NH stretch, right? So there's not going to be anything that's tertiary there. Does the frequency of the carbonyl absorption suggest a carboxylic acid or an ester? Would it be a ketone or an aldehyde, an amide? And I like this because it gives you some references here that you can go back and look at. Does the carbon-carbon absorption suggest an alkene or an aromatic ring? Does the absorption for the triple bond suggest a carbon-carbon triple bond or a carbon-nitrogen triple bond? And you might not be able to tell, and that's okay. He's stretching here to say, is the alkane absorption noticeably weak? That would, of course, suggest that there weren't many CH bonds. I just don't think practically you're going to get much out of this. Then you need to establish whether the carbonyl bond is conjugated. If you have a conjugated carbonyl bond, generally there's also going to be a CC as part of an alkene as part of the structure, or an aromatic ring. Another kind of helpful thing that we are going to use here is the IDH number. So you also, if you're given the molecular formula, you need to calculate the molecule's index of hydrogen deficiency. Now, we did this last semester in chapter 4, so you can go back and you can look at that. And this is just going to tell you how many double bonds, right, triple bonds, or rings. And so this can really help us. For example, if the IDH equals 0, then it's not going to have, say, a carbonyl. That's a double bond, right? It's not just double bonds in between just carbon-carbons, right? There's a double bond there. That would be an IDH of 1. You're not going to have a C double bond O or a triple bond. You won't have a nitrile, and you'll have no ring, right? You'll have a saturated compound. So the IDH number is very, very helpful. Another thing to be aware of, right? And I said IDH, it's IHD, index of hydrogen deficiency. Let's fix that there. If the IHD is lower than 3, right, there will be a no benzene ring. Benzene requires an IDH of 4. I did it again, IHD. Right? 1 for each of the bonds. So there are 3 there, and then 1 for the ring. Remember, talk about IHDs. You always want to, when you're looking at this from the chemical formula, you always want to calculate, right, the number of hydrogens in the saturated molecule. So, for example, if we look here at this unknown, we are given the chemical formula. It's C7H8O. And the first step here that I would do is to figure out the IHD, if you're given that. And so to calculate the number in the saturated molecule of hydrogens, that's going to equal 2N plus 2, where N is the number of carbons, plus the number of nitrogen atoms, right? If you have any nitrogen atoms, minus the number of halogen atoms, if you have any halogen atoms. So that's how we can calculate this. So if we have CnH2n plus 2, I'm going to come down here, I'm going to say, okay, hey, look, that's C7. And so that would be H, 2 times 7 plus 2. Now, there are no nitrogens or halogens, so I don't have to do anything extra here. Oxygens don't affect the number of hydrogen atoms. So that would end up being C7H16. And that's what we would have if that was a completely saturated molecule. So what we're seeing here is that this is not, in fact, a saturated molecule. So what's helpful for us is to figure out how many hydrogens are deficient here, okay? So what we do is we say, okay, we have 8 hydrogens, so I take 16, which is the number we would have if it was saturated, minus 8, and that gives us 8. I divide that by 2, and that tells me my index of hydrogen deficiency is 4. That means we're going to have 4 double bonds, a ring, and 3 double bonds. We are going to have some sort of unsaturation element. So I know this going into this structure. Now, we have a large broad peak right there around 3,300 centimeters. So that's the one I'm talking about there. That's an OH stretch. It's a very characteristic stretch. But notice that oxygen is not going to be part of a C double bond O, because when we look here, right around 1700, right, there's no intense band that's right there. So we can rule that out. That's kind of our step 1, what I would consider step 1. So if we go to step 2, right, do notice that there's an absorption band right around, and I want to do a different color for step 2, right here. So we'll make step 2 blue. And so there's that absorption right about 3050 centimeters to the -1. That's going to belong to an alkene. So it's pretty characteristic of an alkene or an aromatic CH stretch, right? Notice we also have some absorptions right around 1450 to 1600. Those indicate double bonds as well. That's no surprise, right? We've calculated our IDH. We know we're going to have some sort of double bond structure there. And then beyond that, right, we could look for an aromatic ring. An aromatic ring is going to exhibit 2 or 3 peaks in the 1450 to 1600 region. With the IDH of 4, it could indicate a benzene ring, because as we were talking about we do have those peaks kind of right here, okay? So those are pretty indicative, right, of an aromatic ring. Now, beyond that, that's really all you can get here, right? We have some sort of aromatic ring, right, with our IDH of 4 and an alcohol. That's it. So here's our information. It's aromatic, right? It has an IDH, IHD equal to 4, and we've got an alcohol group. Now, we also are given some extra information here, which is it's C7H8O. So there could be a couple different structures here. I'm going to start out by drawing what we think is the aromatic group of benzene. That takes up 6 carbons. That means we're going to have one other carbon. So we'll make that the 7th carbon, and then we're going to have an OH. Now, if I do a count here of all my atoms, right, I have 1, 2, 3, 4, 5, 6, 7 carbons. I have an IDH equal to 4. I have one oxygen group, and it's an alcohol, which is what our IR tells us. And so let's count our hydrogens. There's 2 here, 3, 4, 5, 6, 7, 8. So this would fit this structure. But what you're going to see is there are other things that could fit this structure too. It could be this molecule, right? That also fits. It could be this molecule. That also fits. It could be that molecule. So it could be any of these 4 molecules. That's as much as we can get from our spectra. And honestly, if you don't have this, then you're not going, all you're going to be able to do is say it's got an IDH of 4, it probably is aromatic, and it's got an OH group. You won't be able to elucidate it down to these. What you would have to do is use this in conjunction with your mass spec, and the mass spec would give you the molecular weight of these compounds, and from that you can derive what you believe is going to be the formula. So again, we're using these things in conjunction, but you're not going to be able to figure out a single structure. Let's do another example. So here's our second unknown. Again, we have the structure there. It's C8H14O. Let's go ahead and calculate our IDH for that. C8H2N plus 2. So that would be CHH18. 18 minus 14 equals 4. We take 4, we divide that by 2. That gives us our IHD equal to 2. And so here's some things that tells us. No benzene. Right? And what you don't know is just as helpful as what you do know. I can look at this and say there's no alcohol, right? And that's also really helpful here because we don't have the big stretch here. So we can also look at this immediately out of the gate and say there is no alcohol group there. Let's look at the absorption bands that we have. Let's kind of start over here. We're going to see that we've got the CH stretch here that's between 2,800 to 3,000, right? And so that's that CH stretch. We are going to see that there's a beautiful arrow drawn for us, which is very helpful. At 1682, that is a C double bond O stretch. And then at 1617, that is a C double bond C stretch. Okay, and so those are the stretches that we're going to see. And so what this tells us is that we are probably going to have a C double bond O here. But we can rule out a carboxylic acid or an ester because those require 2 oxygen atoms. So the information we can rule out is just as important as the information that we can identify, right? So the structure here says we only have 1 oxygen. And so we've got a C double bond O. That's probably where that oxygen is. We can also rule out an amide because there are no nitrogen groups here. There aren't going to be any OHs. We've already said that. No alcohols. No, we can also say there's not going to be any NHs. We don't see that stretch. We can also rule out an aldehyde because we don't end up having those aldehyde stretches at right around 27 and 2800, right? So we don't have no aldehyde stretches at, 2720 and these are approximate again because we get some shifts, remember. So we've got a lot of information here of things that we have ruled out. Trying to think if there's anything else that we would suggest. So there's not much else here that is suggested. So it could be a ring, right? But it's probably not super likely. It might be a conjugated ketone. So some good structures then would be like this, okay? You could see a lot of branching, right? But again, if you just walk away from this saying, coming up with structures like this is great, but I would argue that you're just going to be able to walk away from the spectrum saying we have a carbonyl stretch, we've got some CH stretches, and we have a C double bond C stretch, right? And so we could rule out a ring because if we've got a C double bond C stretch and a COO stretch, then our IDH is only 2. There's no way we could have a ring. So you can rule some things out like that. So if you just sit here and say no ring, then that's all valuable information, and you can use the other spectra to tell you other things. So don't be frustrated if you cannot come up with kind of this final spectra that you're looking for. So let's come here to one more unknown, and let's figure out a few things about it. Again, we're not going to come up with a final spectra here, or final compound here. Let's do our IDH number first. So it's C7H13NO. So it would be C7H2N plus 2 plus the number of nitrogen atoms. So when we do that, it's C7H, and 2 times 7 is 14, plus 2, 15, 16. There's 1 hydrogen atom, that's 17, right? And then we take 17 minus 13, and that equals 4, and 4 divided by 2 is 2. So that's our IDH number. So from this, we can rule out some things, right? No benzene, because we have to have an IDH of 4 to at least have benzene. So this can have 2 double bonds, 2 rings, or a triple bond. That's what we have right now. Let's look and see what else we can rule out. We know out of the gate we have no alcohol. That's really helpful to rule out. We see there's an absorption right there around 2800 to 3000. Almost every structure, almost every spectra you look at is going to have that because that's the CH, and these are carbon bonds. Obviously, they're going to have those carbon molecules, so they're going to have that CH stretch. There's also a really sharp peak right there at about 2000, 2000 200 maybe. It's right there in the middle between 2000 and 2500. So that's going to be about where you would get a triple bond or that carbon nitrogen. So remember, there's not a lot else that shows up there in that triple bond region. And so that's what we're going to see there. So we need to go and look at about 3,300. So I'm over here at right around 3,300, and I'm not seeing any sort of alkyne CH stretch. And so what we can do then is we can say, look, it's not going to be a terminal alkyne, because a terminal alkyne is the only one that's going to have that triple bond H stretch. So if we have a triple bond, it has to be a triple bonded carbon. It has to be internal. Now, we've got two an IDH of 2, so it's either going to be the carbon nitrogen or the carbon-carbon triple bond, because each of those would give us an IHD of 2, okay? So at this stage, I would say that's all you can get. You can play around with a few structures if you want, but I would say then you would say, look, we're either going to have a carbon triple bond nitrogen or a carbon triple bond carbon. My guess here, though, is that if I was going out on a limb, is I would say that what we're looking at here is this carbon triple bonded to a nitrogen, just based on the fact that we have a nitrogen there in the formula. And that leads me to believe that because we're not seeing any in H bonds, that we are not seeing any carbon nitrogen single bonds. That's probably what we're going to see there. I also want to point out we don't have any carbonyl bonds, right? Because we don't see anything in that C double bond O stretching frequency for carbonyls. Also, that would take up another IHD number. So there's no way it can be that as well. That might be the only information that you get out of this, and that's completely okay. So we are going to finish up our IR before we go on to UV VIS by just talking just briefly about bending vibrations. I want you to notice that most of the bending vibrations here are in the fingerprint region. Right? Now, these can be useful about a molecule structure, but it's very rare that they're useful. We will not see them at all, really. So very rarely will we see these. We won't use these. If you go on to graduate school, you can, like I said, I use this for one spectra in graduate school to help me identify something. One of the things that's kind of neat is if you do have a spectra that is very clean, then, and it's aromatic, you can tell the difference between ortho, meta, and para, which I think is really interesting. And so you can look here and you can see where you have something that's mono substituted, it tends to give 2 peaks versus a para substituted, which gives 1 peak. So that is one of the ways that you can use that. But again, it's very rare, but it is interesting to file away in case graduate school is your next stop, to know that that region can be used. It's just not generally used until you get into some advanced courses with advanced spectra.